Okay, looking at an example of computing an area using the midpoint rule and also finding the exact area using a definite integral. So this is number 2 in the book, and they give us a picture here. They ask us to find the area below the curve f of x equals 1 over x between 1 and 5. And again, 2 problems here. First of all, they say using the midpoint rule, so we'll start there. Okay. And with the midpoint rule, you can't just say that, you need to tell me how many rectangles to use. So we'll use 4 rectangles. Okay. So how do we do this? Well, again, the idea is this, that we're starting here at 1, we're stopping here at 4. Okay. Whoops, no, not 4, 5. There we go. Okay. So we're stopping, we're trying to find the area between 1 and 5 below this curve. So with the midpoint rule, the first thing you do is you find this thing called delta x, which is the right endpoint minus the left, so 5 minus 1, divided by the number of rectangles you're going to use. And if we're going to use 4, then we take 5 minus 1 over 4, which is 4 over 4, which is 1. Okay, so that means we're going to use 4 rectangles, each of which is going to have a width of 1. Okay, so our first rectangle will go from 1 to 2, the second will go from 2 to 3, the third from 3 to 4, and the last one will go from 4 to 5. So you might even see this in the book that they kind of do this little breakdown here. We need a couple of things though. We need to know our intervals and their midpoints. Okay, because here's kind of the idea that with the midpoint rule, our first rectangle we use is going to be from 1 to 2. It's going to be 1 unit wide. Okay, so it'll start here. Okay, but the height of the rectangle, that's where we have to figure out how we're going to get the height. And with the midpoint rule, we choose the height using this number right here. Okay, this number, which is the midpoint of that first interval. Okay, so our first interval is from 1 to 2. It's our first, I guess we call them sub-intervals. Okay, so between 1 and 2, we have a midpoint of 1.5, right? Okay, and we'll use that number 1.5 to get the height of the curve. Okay, so that's what the height of our rectangle, our first rectangle, is going to be. The width is going to be delta x, which is 1. The height is going to be the y value we get from putting 1.5 into the curve, okay, into the function. So our next interval is from 2 to 3, okay, so 2, 3, okay, and the midpoint there is 2.5, okay. Then we go from 3 to 4, okay. The midpoint there is 3.5, and between 4 and 5, we have a midpoint of 4.5. Okay, so using the midpoint rule, our area is going to be approximately f of our first midpoint, 1.5, okay, times delta x. Okay, and by the way, the book would call this number x1 because it's our first midpoint. Okay, the area of our second rectangle is going to be f of 2.5 times delta x. Okay, the third rectangle, f of 3.5 times delta x. And the area of the last rectangle is f of 4.5 times delta x. Okay, now in our problem, I kind of mixed notations a little bit. I'm putting the actual midpoints in, but really delta x in this problem is just 1. So for instance, to get this answer, what do we need to do? Well, we need to put, for instance, 1.5 into the function. Okay, so that's 1 over 1.5 times delta x, which is 1, plus, okay, we put this number into the function, so 1 over 2.5 times delta x, which is 1, plus 1 over 3.5 times 1, plus 1 over 4.5 times 1. Okay, so whatever that number is, that's what we would approximate the area below the curve, okay, as. Okay, so let's see. Okay, I type it in on the calculator and I get, let's see. Okay, about about 1.5746. Okay, so again, roughly this is what we're computing. We're computing the area of the, well, this is exactly what we're computing. We're computing the area of these 4 rectangles. Okay. The width of each rectangle is delta x, which is just 1, and the height comes from the y value at each one of these midpoints. Okay. So last rectangle, fourth one would be something like this. Okay. And you can see that the area of these rectangles is pretty close to the area below the curve. Okay. So we get about 1.5746 units. Okay. Now, and again, it's always nice when you can do this to check your answer. We could ask ourselves, what's the exact area? Okay. So that's kind of the next question that they ask in the book, the exact area. Okay, well, what about that? Okay. Well, we know that the exact area can be found using a definite integral. We can integrate from 1 to 5 the function 1 over x. Okay. Now this one, it's kind of a piece of cake to integrate because we have a formula for this. The antiderivative, or an antiderivative of 1 over x is natural log of the absolute value of x. Okay. So all we have to do is put these two numbers into natural log and subtract. So the exact area is going to be natural log of 5, the absolute value of 5 technically, minus natural log of the absolute value of 1. And again, now that you see what that is, you can just type it on the calculator. And here's what I get. Okay. Again, that's the exact area, of course, but I'm going to have to round it to a couple of decimal places. So it's about 1.60, let's say 94. Okay, and by the way, since these are areas, I should say square units in my answers. Okay. So really pretty close. We only used 4 rectangles to approximate this area below the curve. Okay, but the 4 rectangles gave us 1.57 square units. The exact answer a little bit bigger, about 1.61, give or take, square units. So, again, a pretty valuable approach for approximating these areas.